Today I will teach you the 5 pillars of good library design in C++. People like to talk about clean code and stuff, but they give abstract examples that don't help anyone. Today I will give practical tips that you can apply when writing any kind of library or system in your C++ code. Also, this video is part of my new 2D library in C++ and OpenGL course. If you want to see these principles used in a full C++ game dev library, check the first link in the description, and it might have a special discount. Principle 1. A good library should be easy to link and integrate. No one will use your library if they can't link to it in the first place. You should make your library as easy to link to as possible. Now, I know you might say, a good programmer won't have problems with linking libraries. But I say that a good programmer will make his library easy to link to in the first place. So remember this, because it's a recurring theme for all pillars of good library design. Whenever you make a bad decision and make your library hard to use in any way, you pass your responsibility to the user when you should be the one fixing that problem. It's your responsibility as a library developer to make your library as easy to use. In this way, developers will also write better code with it. It's easy to blame big corporations for writing bad software, but it's your responsibility as well to write good library code, to also help other programmers write better code. This should be your default number one priority, even more important than code efficiency or speed. Unless of course, your library actually needs top-notch efficiency. Maybe you can sacrifice on how easy it is to use, but otherwise, this should be your number one priority. Back to linking. Your library should be easy to link to, so that beginners can also use it. But also, sometimes, more advanced projects might have weird requirements. Let's look at some examples. You might choose to optimize your library using SIMD. If you don't know what this is, it's basically using some CPU instructions to do multiple operations faster. This is a nice optimization, but it won't compile on ARM processors. So, someone using ARM won't be able to compile your project. Now, I want you to notice that in this example, there are some things that I'm trying to balance. Do I want the library to be optimized? Do I want it to be easily runnable by people with ARM processors? Or do I only care about me running this library? People simply don't ask these questions. So the answer depends on your needs. If you don't care about other people using your library, then you can use these instructions. But at the same time, if this optimization actually turns out to not have a real significant performance boost, it's better to not do it at all. To keep your code simple and not risk breaking things. It's more easy to break things than you think. These instructions might not compile on another compiler, so I would just not use them, rather than gaining a 1% performance increase. Now another example is from the IMGUI library. It allows you to easily make UI for your game, and it's a great library. And adding it to your project is super simple. It has a few header files and CPP files, so all you need to do is add them to your project. That's it. Now, the more complex your library will be, the harder will be for you to make that library easy to link to. But that is not an excuse. There are super big complex libraries that it's easy to link to, and there are also small libraries that have tons of flags and weird things, and it's just a nightmare to link to them. In my 3D rendering library, I wanted to make it as simple to use as possible, so all you have to do to use it is place a CPP file and a header file into your project. That's it. Now this library has external dependencies, a JSON library and a 3D model loading library. Many people would not even bother to include these dependencies in the repo, and they would just mention them in the README. That's horrible. External libraries get updated and changed. You can't just expect the user to go ahead and search for the right dependencies that work with your library. If your library needs external dependencies, at least add them in your repo so people can easily download them along with your library. I like to include them directly into the repo, not as a submodule. You can read this if you want to know why I don't use submodules. With my 3D library, I went a step further and embedded the external dependencies directly into the library. So all you need to do to use my library is place these two files into the project. This type of library is called a header plus source only library, and I recommend it. Usually, header only libraries have a single header file that's then used to also generate a C++ file with it. That is nice, but I think it's cleaner to just make your libraries in one CPP file and one header file if possible. If you have a super big library, then sure, split it into multiple files. But still, try to keep it simple, and at least create a simple CMake for the user that will add those files to the project. With my 3D library, I did quite a lot of work to get here. I have a Python script that merges all my CPP files and also optimizes and embeds the shader files. You don't have to go that far, but you can at least place the dependencies in the repository. And not as a link. The dependency could be updated and changed in the future, or taken down. Place it directly in your repo with the exact version needed to work. Of course, if the library is extremely big, like the Vulkan SDK, you can't place that inside the repo, but most libraries are small. Also, this is not JavaScript. Don't add random dependencies to your library, unless you absolutely need them. So hopefully, you can see that having a big library is not an excuse for having your library hard to link to. You can still ensure that anyone can just download your library and immediately use it. Principle 2. A good library is easy to use. Your library should ideally be so easy to use that people don't even have to read the documentation for it. We will talk more about documentation in a future principle, but let's look at an example. This is how many UI libraries work. In order to create a button, you create a button class, you supply some information to it, like the title, then you also need to supply a callback to it. This is a function that gets called when the button is pressed, and you need to create a separate function for it. Finally, you add that button to some sort of a scene manager. Do you see what the problem is here? Well, let's compare this to how you make the same thing using ImGUI. That's it. You just call a simple function, and you don't even need a callback. You just write what happens if the button is pressed in place. This is so much nicer, because you can reuse variables from above without having to use global variables, and it's so much less code and so much simpler. Trust me, there are many ways of making your code simple. Heavy OOP is usually not one of them, but using simple functions and flags is a good example. I can add flags to this button that alter the button behavior. If I take a look at this function definition, I can super easily figure out how to pass flags and what they do without even having to read the documentation, all from this one function. Also, stay away from callbacks in general, at all cost. Callbacks make code super hard to use and maintain, so you should avoid them as much as possible. Another example, Bullet Physics is a physics library, and it allows you to add 3D shapes debug, so we can see where the actual physical bodies are. This is extremely useful, because the library doesn't do any rendering, it just does physics. So if your object doesn't align correctly with the collider, without a debug view, it would be super hard to fix. But they made this feature extremely easy to integrate in your project. All you need to do is provide them a function that can draw a line, and that's it. Using that one function, Bullet Physics will draw all the shapes it needs. You can provide custom functions for other shapes, but they are all optional. Just one function is enough. Another example, Asimp loads 3D models, and there is a ton of memory management involved here, with textures and 3D models and animations and stuff, so everything loaded by them is tied to the scene object they have. So you can just call a method on it to free all the resources ever allocated by it. I will give you some more examples of easy to use APIs later, while we discuss other pillars. Principle 3. A good API should be hard to use wrong. Many programmers don't understand that code should be easy to use. Many good programmers, probably you included, understand that code should be easy to use. But the best programmers understand that good code is hard to use wrong, and it's totally different from easy to use API. Easy to use API means simple and fast, but hard to break literally means making it hard for the user to do things wrong. Let's look at some examples. The first one is checking for failure points and wrong data often. For example, let's say you have a setVolume function that should have values between 0 and 1. Well, the user could pass wrong values here. So it's important inside the function to clamp the values to 0 and 1. If you get the habit of doing things like this in all your systems, your code will be way more robust. Similarly, if you have a pointer, check if it is a null pointer. And if a function expects to not get a null pointer as a parameter, use a reference instead. You can pass a null pointer to a reference. But things get more interesting. Let's say you have a save image function. It saves your image into multiple formats and resolutions and so on. There is a problem. Not all images files support the same compression methods. Some file formats support a higher compression max value. Others don't support compression at all. Some file formats can't use some flags at all. So the first thing you can do is again, check for invalid parameters inside the function. If the user passed something wrong, you can just correct that. Now you might want to write a comment describing how the function should work correctly. That's good, but you have to understand that comments are not the perfect solution. Besides the fact that people don't read comments, comments are always out of date. Imagine you change this function signature. Well, your compiler will complain because you used your old version somewhere in the code. That's okay, we can now fix it, and the code will compile and work again. But you forgot to change the comment when changing the function, and no compiler can warn you about that. And that will easily happen, trust me. So what can we do? Well, let's just split this big function into smaller functions. Because PNG doesn't have compression, there are no compression options on this function. Now, the user literally can't pass the wrong compression value. It's literally impossible. You see now why this is so powerful? Many people design their APIs in many complex steps, and with many flags. If possible, clamp all of those together. And if you have many flags that have the option to conflict, try to see if you can change that. Trust me, you can think outside the box. Here, for example, I have some 2 flags, and I can specify none, or one of them, but never both of them. So why not change this into some enums? Or here, this function has two optional parameters, but I need to pass both of them if I want to use them. The user can easily pass only one by mistake, and the code will compile. Sure, you can warn the user that he forgot to pass the second parameter. But you can instead make a second function, one that has these two parameters, and both of them are not optional. So whenever you realize there is a way for the user to mess up using your library, try to think if there is a way to fix that. Now of course, some things will depend on the context. I like to return memory managed objects to the user. In general, it's bad to just return row allocated pointers to the user. But if that library is a low level C super high performance library, then you can return a string. Still, in this case, instead of returning an allocated pointer, maybe taking a pointer by the user and the size and writing to that instead. This makes it way more clear that the user manages that memory. Pillar 4. A good library should be versatile. What does versatile mean? Let's say you are making a 2D library that can draw 2D shapes. Well, we are not going to add 3D objects to it, okay? But it would be quite annoying if that library only can draw sprites, but not simple one-color rectangles. Maybe also the option to draw lines or a circle. Now this library has quite a number of features, so it will most likely be good for most people that want to use it. Many people though, when designing a library, make the mistake of adding too many unnecessary features, like an entity system, a complex UI system, a full complex asset manager pipeline, and a particle system. I myself am guilty for adding a particle system to my 2D library. Those are things that the user should do on his own, and if you want to add them, they should probably be different libraries, or at least an optional library extension. That is a good option. So how do you know what features to add? First of all, don't just sit and think what features would be useful. This is a super big mistake, so please pay attention. Just by thinking about what features would be good to add, you will just add useless features. It's simply not possible to predict what is useful and how to design it without actually coding. So you should make projects with this library and find what things are actually useful. For example, this is my 2D rendering library. I initially thought that having a global settings for how I load textures would be a good idea, but after making projects with my library, it turns out it's a bad idea. Also, after making many projects with it, I realized an option to temporarily change the camera is a useful feature. So after you implement the basic features of your library, use the library and see if you are missing something. Also, if you add a feature, like let's say I added the sprite rendering feature into my 2D library, you can, usually, add a simpler version of that, so just rendering a solid color. And now I want to combine pillar 2 with this current pillar, so the code should be easy to use, while at the same time be versatile. This is the most versatile rendering function I have in my library. I can render a sprite with a custom gradient at any rotation I want. The function signature is obviously big because of that. So to make the code also easy to use, I can also make a simpler function that only does some things. Let's say you make an advanced 3D model loading library that can do a ton of things. In order to specify all of these flags, your API will get complicated and there is not much you can do. But you can at least provide a simpler default load model function that the user can quickly use. In Rayleigh, you can render text and load custom fonts. But to print the FPS, Rayleigh provides a quick helper that's just one function and it prints the FPS for you. The user can implement his own FPS print function, but he can also easily use the already made helper. Similarly, you can render quite complex things in Rayleigh, but at the same time, you can just quickly render a rectangle with a simple function. In IMGUI, you can provide a ton of flags to the widgets that they have, but at the same time, you can also quickly use a default button. So try to provide both flexibility to the user, while also providing some quick helpers. Just because your library can do super complex things, it doesn't mean it can't also have some super simple options for quick testing. Quick testing is so important. As a user, I want to check if the library works, and how it works in the least amount of steps possible. If your library takes 200 lines of code to get working, and it doesn't work, I will have no idea what is the problem. Is the library broken? Does the library not work on my PC? Or I did something wrong here? Who knows? Similarly, it's nice to allow the user to pass a custom error reporting function to the library, in case he wants to print those errors somewhere else than the console. Now the final pillar, your library should not enforce something to the user. Many programmers write code in super different ways. People that work on things that should never fail, like airplanes, satellites, or medical equipment, don't use exceptions. Like this feature is literally banned in their team, because it can cause unwanted bugs way too easily. And there are many people, myself included, that never use exceptions, because it's a super bad feature. So using exceptions in your library would kinda force those people to also use them. I simply recommend you to never use exceptions. It's just a bad feature. But if you really want to use it in your library, I recommend adding an option to disable it completely. So it would instead not do any error checkings, or only report them to the console. Many people compile with exceptions turned off on the compiler level, meaning if you throw, the code will just crash, and no one wants their program to crash completely just because the JSON library couldn't read a file and decided to throw because of that. I was in that situation. Instead of throwing an error on fail, just return an empty JSON, and then you can just print the error to the console. Similarly, many people don't use the std string, some use C strings, and others use their own custom strings. So I like to take string parameters as C strings, so anyone can use my functions easily. Let's say you make a function that reads an entire file. I like to simply return that file into a string for convenience. Principle 2. Make the API easy to use. But some people might not want to use the string, so I can also make a function that reads that file into a buffer instead. Another example, SFML is a drawing library, but to render a simple shape on the screen, you need to create a sprite object, set its position and texture, and render it. I don't really like this, because I already store my player's position in a physics struct made by me. Why should I go through this extra stuff here to store my position again? So my 2D rendering library just uses a function that takes the position as a parameter. If the user wants to use a sprite class like SFML, he can extremely easily implement one himself and make it suit his own needs. But I provide the simplest implementation possible, so anyone can use it however they want. Let's say you want to load a 2D texture. Usually, you'd have a load feature. You give the path to the file, and the library loads it for you. That's super nice to use, but at the same time, you are forcing the user to load the texture from disk, using a file. What if someone wants to load files himself, and then load the file from there? So it's good to provide both of these features. This version provides an easy to use version, while this one provides flexibility. And I know you might say, who would not want to simply use this function and load the images from disk? But you might be surprised. Maybe someone wants to embed an image into the code. Or in my game engine, for example, files can only be opened in a specific way, otherwise the code crashes. So not having the option to open the file myself would never work in my game engine. Finally, another nice thing to have is the option to provide a custom memory allocator to the library, or ways to use the library where the library never allocates memory. This is super helpful, especially in game dev, but it's also harder to do, and you may have to sacrifice on other things instead. So I would say don't think about this for now. But at least, as a bonus tip, try to never simply return random allocated pointers. This is just asking for memory leaks. If you return a small object, and yes, this is small, return it on the stack, or return C++ objects that manage memory, or ask the user to allocate the memory himself by taking in an array. These are all the pillars, but you will actually learn them with practice. If you like this kind of tips, make sure you subscribe for more. And also, check the first in the description for my 2D library in C++ and OpenGL course. I cover batch rendering, text rendering, and we fix this texture atlas bug, with 20 plus guided challenges for you. And besides, I highlight the pillars I talked about in this video, so you get to use them in a real project. If you are planning to make a game engine or make a game from scratch, this course is a great start. See you there.